Hey there, and welcome to the Deep Dive. So glad you're joining us for this exploration.
Great to be here.
Today, we're tackling something uh, absolutely critical for the future of a technology you hear about constantly, blockchain.
That's right. We've all been captivated by the potential, these decentralized, secure systems. But for blockchain to move beyond niche applications and truly integrate into the high volume demands of the real world, it faces a major hurdle.
And that hurdle is scalability. It sounds simple, maybe,
Yeah.
but in the world of blockchain, what does scalability really mean?
Well, at its core, it's about performance under pressure. How well does a blockchain system cope when more and more people start using it? Can it handle an increasing number of transactions and a growing amount of data while still being, fast, affordable, and efficient?
Because right now, if you ever tried to use a popular blockchain network when traffic is high, fast, and affordable, might not be the first words that come to mind.
Exactly. You sent us a stack of really insightful materials for this deep dive, including a really comprehensive review paper on blockchain scalability, plus pieces on mobile edge computing, smart contracts, state channels, and even something as cutting edge as zero-knowledge proofs.
Yeah, quite a bit to get through.
So our mission today is to cut through all of that, extract the most important insights, and understand the fundamental complexities of the scalability problem and the diverse, often ingenious ways people are trying to solve it.
All right, let's get straight to the heart of the problem then.
Yeah.
Why is it so hard for blockchains to scale? What is it about their design that creates this bottleneck?
Well, the very features that make blockchain appealing, decentralization and security, also create limitations. For the network to be secure and for everyone to agree on the truth, every single transaction typically has to be processed and validated by most, if not all, participants in the network.
Right, everyone needs a copy,
Yeah.
essentially.
Exactly. And as transaction data grows and the number of users and network nodes increases, this global validation process becomes incredibly inefficient.
So it's like trying to get everyone in a huge city to agree on every single traffic decision in real time. It just grinds to a halt.
That's a perfect analogy. And that inefficiency, it shows up in several ways that directly impact you as a user or developer. You see slow transaction processing, which is high latency.
Waiting ages for confirmations.
Right. You experience low transaction throughput, that's the limited number of transactions per second the network can handle. And when demand is high, you get those often eye-watering transaction fees because everyone is competing for limited block space.
Yeah, the gas phase.
Yeah. And on top of that, requiring every node to store the entire history of the blockchain and constantly communicate new data, well, that increases storage and bandwidth requirements. As our sources point out, these issues significantly hinder widespread adoption in practical environments.
And the difference between blockchain and traditional systems is just staggering, isn't it? I saw a comparison in the material. A major network like Ethereum might process around, what, 14 transactions per second?
Something like that, yeah. Maybe a bit more sometimes, but in that ballpark. While a traditional payment processor like Visa can handle tens of thousands, up to maybe 24,000 transactions per second, that gulf really illustrates the scale of the challenge we're discussing.
Wow. It's enormous. And this even impacts smart contracts, these automated agreements that are supposed to bring so much functionality.
Absolutely. Smart contracts are code that runs on the blockchain. So if the underlying blockchain is slow, expensive, or congested, the smart contract inherits those limitations. Their full potential for complex applications is directly constrained by the scalability of the platform they live on.
Okay, so we understand the problem and its impact. Pretty significant. Before we jump into the solutions, maybe let's quickly touch on the fundamental pieces that make up a blockchain, because the solutions often target specific parts of this architecture. What are these core building blocks?
Yeah, good idea. The comprehensive review paper breaks it down nicely into layers. There's the data layer, how information is actually structured and stored.
Okay.
The network layer, how all the different computers or nodes communicate with each other. The consensus layer, perhaps the most critical, this is the mechanism by which all those distributed nodes agree on the correct state of the ledger.
The agreement part.
Right. Then the execution layer, where transactions and smart contracts are actually processed. And finally, the application layer, which is closer to what you and I interact with, like wallets or decentralized apps. Scalability solutions can focus on optimizing or changing any of these layers.
And the data structure itself isn't always the familiar chain of blocks is it? We have the classic blockchain.
Yes, the traditional blockchain, like in Figure 1 of the review, is a sequence of blocks, each containing a bundle of verified transactions. These blocks are linked cryptographically using hashes, creating that immutable history. Adding new blocks requires a consensus process, typically involving miners or validators.
But then there's something called the DAG, a directed acyclic graph. Sounds complicated.
It's a different approach. A DAG, like the one shown in Figure 2, fundamentally changes the data structure. Instead of a linear chain, it's more like a graph where individual transactions validate previous transactions directly.
Ah, okay. Not block by block.
Exactly. Think of it as a web of transactions building on each other. Networks like IoT's Tangle or Nano use this structure. The idea is that new transactions contribute to validating the network, potentially leading to faster confirmation times and throughput that could theoretically increase as the network grows. You're sort of removing the bottleneck of bundling transactions into blocks by validator.
Okay, that makes sense. A different way to structure the data. And how transactions are represented or processed also differs. UTXO versus account-based.
Yeah, those are the two main models. UTXO, or unspent transaction output, is the model Bitcoin uses. Assets aren't held in accounts with balances like a bank. They're represented as these fragmented outputs from previous transactions.
Like digital spare change.
Kind of, yeah. When you spend Bitcoin, you select these unspent outputs and create new outputs. This model can actually facilitate parallel processing, which is good for simple value transfers.
And account-based, like Ethereum uses.
That's more familiar, I think, if you think about traditional bank accounts. Each account has a balance, and transactions involve debiting one account and crediting another in a global state ledger. This model is generally simpler for representing the complex state changes needed for smart contracts.
Right.
However, maintaining and scaling this single global state can be more challenging than the UTXO model, though it's often better suited for complex applications that need state information beyond just balances.
Got it. Problem defined, building blocks understood. Now the big question, how are people trying to fix this? The comprehensive review categorizes the solutions into 5 major areas. What are the...
Yes, the paper provides a very useful taxonomy, Figure 3, I think it was. They group the efforts into on-chain scalability, off-chain scalability, often called Layer 2, scalable consensus mechanisms, DAG-based scalability, treating DAGs as a solution approach itself, not just a data structure, and horizontal scalability, most notably sharding.
Wow, okay. 5 big categories.
And each targets different aspects to improve metrics like, how many transactions per second, how fast they confirm, how much data is sent, and how much storage is needed.
Let's start with on-chain. This sounds like modifying the core engine itself, the main blockchain.
Precisely. These are changes made directly to the fundamental rules or structure of the blockchain protocol. One straightforward approach is simply increasing the size of blocks, like Bitcoin Cash did.
Okay, put more transactions in each block. That seems obvious. What's the catch?
Well, the catch is often decentralization. Larger blocks mean nodes need more storage and bandwidth to download and verify them. This can make it harder and more expensive for ordinary individuals to run a full node, potentially leading to fewer nodes and thus a more centralized network. It's a trade-off. Another example is segregated witness, or SegWit, which Bitcoin and Litecoin implemented.
Ah, SegWit. I've heard of that. My understanding is it separates signature data somehow.
That's the key innovation, yes. It moves the witness data, primarily transaction signatures, out of the main part of the transaction data stored within a block. This effectively frees up space in the block, allowing more transactions to fit in.
So more transactions per block, but differently.
Exactly. It speeds up confirmation times for dependent transactions and also, importantly, enabled the development of certain off-chain solutions like Lightning.
And the trade-off with SegWit. Is there one?
Well, because it was implemented as a soft fork, meaning older nodes still function but don't fully validate the segregated data, some argue it can potentially introduce complexities around, say, transaction fungibility if not all network participants adopt it. It also increases the overall data processed by the network, even if it saves space within the traditional block structure.
Okay. The sources also mention data reduction techniques.
Right, like compressing the blockchain history. Techniques like Texome aim to compress block data to reduce bandwidth and storage needs. Other approaches like segment blockchain or SE chain focus on storage specifically, allowing nodes to maybe only store parts of the chain's history rather than the full ledger, reducing storage requirements for individual nodes.
Okay, so on-chain is about tweaks to the core chain. What about off-chain? Or layer 2 solutions. This feels like building, I don't know, parallel systems.
That's a good way to think about it. These solutions move the vast majority of transactions off the main blockchain, processing them quickly and cheaply elsewhere. The main chain is only used for critical functions, like opening and closing these off-chain channels, or, crucially, resolving disputes.
Let's do most of the work somewhere else.
Exactly. The goal is high-volume, low-cost activity away from the core bottleneck.
Payment channels sound like a classic example here, like the Lightning Network for Bitcoin.
Absolutely. With a payment channel, two parties lock funds on the main chain to open a channel. They can then send transactions back and forth, basically instantly and for free, off-chain, without touching the main blockchain for each individual payment.
Wow, okay.
Only the final state, when the channel is closed, or if there's a dispute, is broadcast back to the main chain for final settlement. Our sources mention Lightning, Raiden, Trinity, and also Rapido, which is noted for offering multipath payments, letting you send value even if you don't have a direct channel open with the recipient.
Interesting. And sidechains are another layer 2 approach. How are they different?
Yes, sidechains are entirely separate blockchains that are linked to the main chain, using a mechanism that allows assets to be transferred back and forth, often called a two-way peg.
Yeah.
They can have different rules, different consensus mechanisms, or different block sizes optimized for specific use cases.
So you could have a sidechain designed just for gaming items, maybe?
Potentially, yes. Plasma, for example, is a framework for creating hierarchical child chains layered on top of a main chain like Ethereum. But they introduce complexity. You need to secure the sidechain itself, and the process of moving assets back and forth, that pegging mechanism, can have security considerations. The sources note that Plasma, in particular, requires careful design to ensure the security and immutability of those child chains.
Right, complexity seems to be a running theme. Okay, so layer 1, on-chain, and layer 2, off-chain solutions target the data and network layers, maybe touching the execution layer. What about the consensus layer? That sounds like a fundamental bottleneck, how everyone agrees.
It is indeed a major bottleneck, consistently highlighted across the sources. The consensus mechanism, the way nodes reach agreement on the next state of the ledger, really dictates how quickly and how many transactions can be confirmed.
We're most familiar with proof of work and proof of stake. How do they impact this?
Well, proof of work, PoW, used by Bitcoin and originally Ethereum, relies on computational power and, lots of energy. It's very secure against certain attacks, but it's inherently slow because of the difficulty of the mining puzzle.
Yeah, the energy usage is a big topic.
Definitely. Proof of stake, POS, which Ethereum is moving towards, replaces that computational work with economic stake validators are chosen based on how much cryptocurrency they hold and are willing to stake. This is far more energy efficient and can offer lower transaction latency and potentially higher throughput.
Sounds better.
But it comes with different security considerations, like potentially being more vulnerable to Sybil attacks, if not designed robustly, as the sources mentioned.
Yeah.
Where someone tries to gain control by creating lots of fake identities.
Okay, different trade-offs again.
Yeah.
And then there are the BFT-based consensus mechanisms. Byzantine fault tolerance.
Yes, BFT-based systems. These are consensus protocols designed to work even if some participants are malicious or unreliable, up to a certain threshold. Variants like PBFT, DPoS, delegated proof of stake, FBA, or DBFT are common in permission blockchains like Hyperledger Fabric or used in projects like Zilliqa, Ripple, Stellar, Neo, and EOS. These generally offer high throughput and low latency because they involve direct communication and voting among a known or smaller set of participants.
Sounds fast. What prevents them from being used everywhere then, especially in big public chains?
They are very communication intensive. Every node or validator needs to talk to many other nodes frequently. This scales poorly in large, public, permissionless networks where there are thousands of unknown participants constantly joining and leaving. They are often better suited for environments with a limited, known, and relatively trustworthy set of validators.
Oh, okay.
DPoS specifically addresses this somewhat by having token holders elect a smaller set of delegates to perform the validation, kind of like a representative democracy.
Okay, so consensus mechanism is a massive piece of the scalability puzzle. We touched on DAGs as a data structure earlier, but they also represent a fundamentally different approach to achieving consensus, don't they? Not just data structure.
They do, yeah. The DAG structure itself enables a different consensus pattern. Instead of block-by-block agreement through mining or staking, confirmation is often achieved by new transactions referencing and validating previous transactions directly.
So validation is more distributed and continuous.
Kind of, yes. Networks like IoT's Tangle are built on this principle, designed specifically for the Internet of Things, aiming for feeless transactions and throughput that could theoretically increase with network usage. Nano uses a variation called a block lattice, where each user has their own chain, and transactions are confirmed asynchronously.
Sounds efficient, potentially. Any downsides?
Well, the sources note that while DAG systems promise speed, they still grapple with complex challenges to ensure the same level of security, consistency, and finality as traditional blockchains. Balancing performance with protection against malicious activity is still tricky.
Right. That brings us to the final major category from the review, horizontal scalability, which is often discussed as sharding. This seems like a really promising avenue. A lot of buzz around sharding.
It's widely regarded as one of the most significant approaches for scaling blockchains horizontally, yes. Sharding involves partitioning the blockchain network and its data into smaller, more manageable pieces called shards.
Okay.
Each shard can then process transactions and manage its own piece of the state independently and in parallel.
So instead of everyone processing everything, different groups handle different subsets of the work simultaneously, like splitting that single-lane highway into multiple independent highways.
Precisely that. Figure 12 in the review gives a good visual of this partitioning. By processing transactions in parallel across shards, the overall transaction throughput of the system can be dramatically increased.
Which projects are doing this?
Early research prototypes like Elastico pioneered the idea. Omna Ledger focused on secure, scale-out sharding, using techniques like bias-resistant randomness to assign nodes to shards securely. RapidChain aimed for robustness, even if a significant portion of nodes were malicious. Zilliqa also implemented sharding, focusing on transaction processing but facing challenges with state sharding. That's how to manage data when different shards need to access information stored on another shard.
Yeah, that sounds complicated.
It is. Projects like Harmony aim for full sharding, partitioning not just transactions but also network communication and storage, often combining sharding with proof of stake and efficient BFT consensus. Monoxide proposed consensus zones based on transaction addresses.
Sharding sounds powerful because of the parallel processing. What are the main complexities or trade-offs there?
The biggest complexities lie in coordinating across shards. What happens when a transaction involves assets or smart contracts on different shards? How do you securely communicate between shards? How do you ensure the overall consistency and security of the network when individual nodes only hold the state for their specific shard, not the entire global state? These are really active areas of research and development.
Okay. We've covered the main solution categories. Let's circle back to smart contracts briefly. We mentioned their potential is limited by blockchain scalability, but they also have their own inherent challenges, right?
They absolutely do. Smart contracts are powerful because they're self-executing code, but that code is often deployed onto an immutable ledger.
Meaning if there's a bug, it's set in stone. You can't just patch it.
Essentially, yes. Often you can't. This irreversible nature, combined with the complexity of coding secure decentralized logic, has led to some significant vulnerabilities. The sources highlight infamous cases like the DAO attack, caused by a re-entrancy vulnerability in the smart contract code.
I remember that. Big deal.
Huge. And the Smart Billions hack, which manipulated elements like the block hash. These incidents underscore the critical need for rigorous security auditing and testing before deployment. There's also the challenge of smart contracts needing external data, things like stock prices or weather data brought in by oracles.
Right, getting real-world info onto the chain.
Exactly. And if these oracles are unreliable or compromised, the smart contract can execute based on faulty information, which can be disastrous.
Are there specific solutions being developed just for smart contracts security and efficiency, separate from scaling the underlying chain?
Yes, definitely. The sources mention tools like formal verification, using mathematical methods to prove properties about the code before it's deployed. Tools like Truffle or Oyente aim to catch bugs early. There are also performance optimization techniques and tools like Gas Reducer to make code more efficient and cheaper to run, or methods to enable parallel execution of certain smart contracts. Security tools exist to detect vulnerabilities like Contract Fuzzer or Regard, or even add privacy features like Hawk.
So, solving scalability isn't just about the base layer. It's also about making the applications running on it more robust and efficient.
It's absolutely a multi-layered problem requiring solutions at different levels of the stack. You need both.
Now, looking ahead, there are some really exciting emerging technologies mentioned. Zero-knowledge proofs came up in the materials. This sounds incredibly futuristic, almost like magic.
It does sound like it. And the concept is quite elegant, really. A zero-knowledge proof, ZKP, allows one party, the prover, to prove to another party, the verifier, that a statement is true without revealing any information about the statement itself beyond its validity.
Okay, hang on. Prove something is true without showing the proof.
Sort of, without showing the underlying data that makes it true. Imagine proving you are eligible for a service like you're over 18 without ever having to show your actual date of birth to the verifier.
Okay, I think I get it. So it's fundamentally about privacy. But how does this help with scalability? That seems like a leap.
This is where ZKPs get really interesting for scalability. They enable powerful layer 2 techniques like zero-knowledge rollups. With a rollup, a large batch of transactions is processed and executed off-chain.
Right, like other layer 2s.
But then a ZKP is generated that cryptographically proves that all of those off-chain transactions were valid according to the rules of the system.
And instead of posting every single one of those transactions on the main chain.
You post just that single compact proof. The main chain only needs to verify the proof itself, which is much, much faster and cheaper than processing thousands of individual transactions. This dramatically reduces the data and computation burden on the main chain, leading to significantly higher effective throughput.
Wow, that's clever.
It is. Our source even suggests that technologies like ZKPs could usher in a blockchain 2.0, shifting the paradigm from requiring full transparency for all data to relying on privacy-preserving cryptographic proofs to verify validity. This is pretty essential for bringing sensitive data and more complex applications onto blockchain systems safely.
That's a fundamental shift in how we think about trust and verification on a blockchain. And ZKPs have applications beyond just scaling transactions.
Oh, absolutely. They're being explored across numerous sectors mentioned in the source, things like supply chains to verify product authenticity without revealing proprietary sourcing details, digital identity to prove attributes without disclosing your core identity documents, digital finance for confidential transactions, and even in biometrics. It's a very active area.
Wow. So we've taken quite a deep dive today into the critical challenge of blockchain scalability. We've seen how the core design, creates these bottlenecks and explored a vast landscape of solutions.
A really wide range.
Yeah. Modifying the core protocol with things like bigger blocks or SegWit, moving activity off-chain with payment channels or side chains, developing faster consensus mechanisms, leveraging different data structures like DAGs, partitioning the network with sharding, making smart contracts themselves more robust, and even using advanced cryptography like zero-knowledge proofs to enable entirely new scaling paradigms like rollups.
Phew. It's clear from all this material that there isn't one single silver bullet answer. It's a complex engineering problem, and the research and development efforts involve exploring multiple avenues, often combining different approaches, and constantly navigating those inherent trade-offs between scalability, security, and decentralization.
And understanding this isn't just academic, right? For you, whether you're interested in using, building on, or simply understanding blockchain technology and decentralized applications, grasping these challenges and the clever solutions being developed is key to seeing the real potential and the current limitations of this technology. It shows us how this technology might actually reach the scale needed for everyday use.
It truly highlights the dynamism and the sheer innovation happening in this space. It's moving fast.
Well, that was quite the journey into the depths of blockchain scalability. Thanks for guiding us through these sources. That was really insightful.
My pleasure. Always fascinating stuff.
And thank you for joining us on this deep dive. It's remarkable to see the breadth and creativity of the solutions being pursued to tackle this critical problem.
Indeed it is. A lot of smart people working on this.
So let's leave you with a thought to ponder as you go about your day. With so many different approaches being developed on-chain, off-chain, new consensus, sharding, ZKPs, which path, or perhaps a clever combination we haven't even fully envisioned yet, do you think holds the ultimate key to unlocking true mass adoption for blockchain technology? And maybe what level of compromise on the ideals of decentralization or security are we truly willing to accept for the sake of speed and scale? Something to think about.
That is a crucial question for the future, isn't it?
Absolutely. Until next time, keep digging deeper.